Welcome back to this lecture series on concurrency state models and design patterns. Today we're going to take a rather different tack and we're going to see a different kind of formalism for modeling and understanding concurrency, known as PetriNets. The presentation today is based mainly on this classic article by Peterson on PetriNets theory and the modeling of systems. The outline for today is as follows. I'll start with an introduction to PetriNets and how they're defined as a graph model that can be incrementally updated, a little bit similar to, yet different from finite state automata. And then we'll see a series of examples looking at how we can use PetriNets to model different aspects of concurrency and synchronization. Then we'll have a look at some of the formal properties of PetriNets, which are quite interesting, particularly liveness and boundedness. And finally, we'll have a brief look at different ways of implementing PetriNet models. So for starters, let's have a look and see how PetriNets are defined. So PetriNets were actually originally called nets. They were invented by Carl Adam Petri, a German mathematician. But after he introduced them, they were always referred to as PetriNets. And they have turned out to be especially interesting for modeling concurrency in computer systems. So a net is kind of a graph model. It consists of a static part and an updatable part. So the PetriNet consists of two sets. So it's a bigraph consisting of places and transitions. In addition, there are input and output functions which show how we map from bags of places to transitions and from transitions to places. Finally, there's a dynamic part which is a marking, which is a mapping from places to a number of tokens. It's perhaps easier to see with an example. So we see here on the left-hand side the formal definition of this PetriNet, and on the right-hand side, a graph-based representation. So places, here we have a set of places which are X and Y, and they're usually represented as circles. Then we have transitions. So the transitions here are A and B, and they're usually represented as flat bars or rectangles. The idea is that the transitions can fire, and what they try and do is they try and consume tokens from their input places and then produce tokens in their output places. Every transition has synchronizes because it can have multiple inputs and multiple outputs. So there's a static part of the graph here, which is the set of places and transitions and the input and output functions. So the inputs for A here is just X, as we see in the formal definition, and we see one arrow from X to A. And the input of B actually takes two inputs from X. The outputs of A sends one output to X and one output to Y, and that's represented here as a bag. So formally, the output function and the input function map a transition to bags of places. So that's essentially a mapping from the set of places to natural numbers. So it's a formal way of representing a bag to say how many instances do we have of this particular object. So here we'll have two instances of X as the input, and here just one input of X. Finally, we have the dynamic part, which is the marking. The marking is a mapping from places to natural numbers. So it represents essentially a bag. It says, how many tokens do we have in each of these places? So here we've represented it this way as a bag, saying, okay, well, we have 2 tokens X and 0 tokens in Y. We could have also represented it as a function, mapping from X to 2 and Y to 0. So we have the static graph model of the PetriNet, and we have the marking, which is an assignment of tokens to the places of the PetriNet. Now the interesting part is when we can fire transitions. Basically the idea is any transition which has all of its inputs satisfied, so there are enough tokens in each of its input places, then it is fireable. And then we pick one of these transitions to fire, and this will consume all of the inputs from its input places, and it will generate outputs in the output places. That is, it's going to rewrite the marking to a new one. So here we see there are two parts to firing a transition. First of all, a transition must be enabled. That is, the marking, which is a bag, has to be greater than or equal to the inputs of that transition, which is also a bag. So that means all of the elements that we're expecting as input exist in this marking. Here we see the enabled transitions because transition A wants one input from X here, and there is at least one token in the marking, and B here also wants inputs. Actually, it wants two tokens, and there are two tokens. So we've colored both of these transitions red to indicate that they're hot, they're ready to fire. And the second part is we pick one of these transitions to fire, and what happens is we generate a new marking by subtracting the inputs and adding the outputs. So that's a very simple operation. So in this state, either transition A can fire or transition B can fire. If transition A fires, it will consume one input from place X and produce an output in X and an output in Y. So here we see the new state, which is like the old state, except we have an additional token in place Y. If we, on the other hand, fire transition B, then B will consume both tokens in X and produce one output in Y. Notice that after firing A, both A and B are still enabled. However, after firing B, both A and B are now disabled, and the PetriNet now is deadlocked. It can make no further actions. Following along the top line, once again, transitions A and B can both fire. If we fire A, then A will consume a token from X and produce one in X and one in Y. So now we have two tokens in Y. If we fire B, on the other hand, we'll consume both tokens in X, and now we'll terminate, because now A and B are once again disabled, and we have two tokens in Y instead of one. And then, once again, A or B can fire, and so on down the line. Notice that there is a sequence of possible terminal states with all possible values of, so the terminal markings are those where X has no tokens and Y has some integer number of tokens, non-zero number. Whereas along the top line, we have all possible integer values of tokens in Y and two tokens in X. So these are all the possible reachable markings. So that's basically what there is to the standard model of PetriNets. Now let's see what we can do with this. PetriNets can be used for modeling concurrency, because we can model concurrently enabled transitions which can fire, and also synchronization, because transitions compete for tokens which are sitting in shared places. The PetriNet itself is uninterpreted. That means that it's up to us what places and transitions and tokens mean. So we can use tokens to represent, for example, the availability of resources. A token is sitting in a place, and it means we use it to model the fact that various transitions want to have mutually exclusive access to them. Or a token could mean that it's a task, a job to be performed. We have a queue of tasks sitting in a place, and various workers, which are transitions, can grab these tasks and perform them. Or a token can mean this is where we are currently in a workflow. So the token can move and flow through the network, showing where something is actively happening. Or a token could represent a more complex kind of synchronization condition. We'll see a few examples of these. Here's an example of pure independent concurrency. We have two transitions which can fire and fire independently. The one on the top is enabled because it requires one input from each of its places, and there's at least one token in each of those places, so it's enabled. And the one below is also enabled, and there's no competition between them, so they can actually fire concurrently. In PetriNets, in the standard model, however, we can only make one step at a time. So we pick one transition to fire it, and then pick another one. However, there can be other models of PetriNets where we can fire multiple transitions concurrently if they do not compete. So here we can fire both of these transitions, and now nothing is enabled anymore, so the PetriNet has reached its terminal state. Here we have a slightly different net, similar but slightly different, but now transitions A and B share an input. So the place on the left in the middle, that means both A and B are enabled, but only one of the two could fire. We could fire A or we could fire B. So if you fire B, for example, then B consumes the shared token and A is now disabled. So even though it could have fired, it didn't. And in this particular execution path, it's been disabled and can no longer fire. Here we have an example where we're modeling mutual exclusion. We have two subnets. So the actual net is just the part in the middle, and the big boxes on the outside, these are not formally part of the PetriNet. They're just pictures here to help us visualize that there are subnets which are interacting. So basically the idea here is that we have a subnet which is looping around. This token is representing flow of control. If this transition fires, it'll move here and then it'll move back again. Similarly, here we have a token representing flow of control. This token, on the other hand, is behaving like a semaphore. In other words, here, these parts of these subnets can be considered to be critical sections. So this token here is representing either a shared resource or a semaphore. So in order to enter the critical section, this subnet on the left needs not only its flow of control to be activated, but it also needs this token to be available, the shared one. Now, if we fire one of these subnets, for example, the one on the left, the token in the middle disappears, and we have a flow of control in our critical section. Once this subnet proceeds, then the shared token gets put back. Notice that at this point, there's only one transition that's enabled in the whole net, which is the one at the bottom at the left. The subnet on the right has been disabled because the shared token is no longer available. If the first one loops around, however, now suddenly the shared token is available and the subnet on the right is also enabled. So now we have, once again, two transitions which can fire. So now this one can get a chance and loop around. Notice that when it did that, the subnet on the left was temporarily disabled. Now here's a somewhat abstract PetriNet. We have illustrated here on the left-hand side, we have a transition which is waiting for a flow of control to come in, and when it fires, it will place a token on each of its output, which is going to enable these three subnets. Notice that these are just boxes, so this is not formally a complete or correct PetriNet, but we've kind of covered up the subnets with pieces of paper, if you will. So you can imagine that there's more subnet going on inside here. And the idea is that once this token is available here, this net will be enabled and will start running. Same with the other two. When they've all completed, they'll place tokens here at their outputs, enabling this transition, which is waiting for all of the subnets to finish before it can terminate. So here, if we fire the first transition, we have then 3 subnets which are all enabled. They can start executing. When they terminate, they place tokens in their outputs. And finally, we have the join transition, which will wait for everything to terminate and then come to its end. Here's another example of producers and consumers. Here again, we have 2 subnets, one which is a producer and the other is a consumer. The idea here is that the consumer is waiting for enough tokens to be produced that it can start consuming them and doing some work too. The producer loops around, and every time it produces something, it provides a token for the consumer to start working. Notice that the producer can run ahead of the consumer and produce as many tokens as it likes. The consumer can take its time consuming these tokens at its leisure. But it's never possible for the consumer, of course, to run ahead of the producer. Producer can run ahead of the consumer, but not vice versa. Now, if we want to avoid that the consumer runs ahead, the producer runs ahead of the consumer, instead of having an unbounded buffer, as we had in the previous example, we can introduce a bounded buffer. This requires a little bit more effort in modeling, but it's actually pretty simple too. Here, the idea is the following. We have tokens that represent occupied slots and free slots. Here, in this particular case, there are 4 tokens ready for the consumer to start consuming. The producer, on the other hand, can only produce up to 4 tokens because it needs a free slot. Once a slot is free, it will grab it, produce something, and turn it into an occupied slot. So in this particular case, the producer can never get ahead of the consumer, and vice versa. Let's see it in action. Here the producer wants to produce something, but it can't because there are no free slots available. So now the only thing that can happen is that the consumer can start working. So it can loop around. Notice now that there are free slots available, the producer is enabled. So it could, if it wanted to, if it got scheduled, then it would start to loop around and produce something as well. So here, the consumer started running ahead, and now the consumer has consumed all the occupied slots, and now it's blocked. So the consumer as well can't get ahead of the producer. Now the only thing that can happen is that the producer will consume a free slot and put something and make it available for the consumer. That's all very fine and dandy. It's very nice mathematical formalism, which lends itself very well to visualization and animation. However, what can we do with this? What kind of properties can we analyze? I mentioned the term reachability earlier, but I didn't explain exactly what I meant. The reachability set of a net is a set of all markings that you can reach from an initial marking M. If you recall, the very first PetriNet that we saw started with an initial marking with 2 tokens in the X place, and then it could fire a B transition at any place or any number of A transitions and then a B transition. And then we saw that we generated that way a large number of different possible markings. The enabled ones with 2 X's and any number of Y's, and the terminated ones with 0 X's and any number of non-zero number of Y's. And that's an infinite reachability set. Now there's some interesting properties of nets. A net that has an initial marking M is safe if every place holds at most 1 token. So that means it's bounded in a certain way. We can never have any more tokens than we have places. A marked net is K-bounded if each place never holds more than K tokens. So a safe net is simply a 1-bounded net. And a marked net is conservative if the total number of tokens is constant. Now at this point, what I would like you to do is go back and have a look at all of the nets, all of the examples we saw up until now, and try and decide for each net whether it's k-bounded, whether it's conservative, whether it's safe, and what its reachability set looks like. Now, if you've done that exercise, let's continue ahead and have a look at two more important definitions, namely liveness and deadlock. So liveness and deadlock are closely related in PetriNets to the notions of liveness and deadlock that we saw earlier in FSP. So a transition is deadlocked if it can never fire. A transition is live if it can never deadlock. So this is very closely related to progress properties in FSP and LTSA. So here's an example of a net that is both safe and conservative. So this net has transition B, which is enabled. If B fires, a token will be consumed from place Y and produced in Z. Then C will be enabled and would just loop around. So this token is going to loop around between transitions B and C. Transition A is deadlocked because it can't ever fire, because there's no token in X and there's no way to ever get a token in X. Firing B and C repeatedly will produce two possible markings. There's one marking with the bag Y, so a single token in Y, and there's one marking with a single token in Z. So there are actually two possible markings in the reachability set, so that's quite tiny. So the reachability set is the set of bags where one bag has just a token Y and the other one has a token Z. Notice that the net here is safe. We never have more than one token in any place, and it's conservative. We always have exactly one token in the net as a whole. Now there's another exercise that you can do, is go back and have a look at all of the examples and check additionally, are they live and which transitions are deadlocked. Now PetriNets, as you might think, are closely related to the finite state processes that we've seen many times now in conjunction with LTSA. Finite state processes are essentially equivalent to regular expressions, and we can model finite state processes as one token conservative nets. The single token represents the state of the finite state process. The places represent the states, and transitions represent the actions that can be performed. So here's a regular expression A, B, or C star D, and it can be modeled quite easily as a finite state automaton, which is quite clear, but finite state automata and finite state processes are essentially the same thing at the lowest level. It's just that finite state processes have additional features related to concurrency, which allows them to be analyzed and composed in interesting ways. Now this finite state automaton, which can also be thought of as a finite state process, is equivalent to a PetriNet, and we can turn this into a PetriNet in a trivial way. Simply take each of these arrows, add a transition in the middle. So now we have break each arrow into two arrows and place a token in the initially enabled state. And now suddenly, presto, we have a PetriNet. So any finite state process and also any finite state automaton can be trivially modeled by a one token conservative net. We have a single token which is always moving through the PetriNet, showing which place is the currently activated state. Now, some PetriNets can be modeled by finite state processes. Here, for example, we have a PetriNet on the left, and this PetriNet has we have essentially two subnets which are synchronized here with a common transition, and they're basically looping around here. In order for the transition C to fire, however, we must have tokens in both V and X that fire in tandem. But other than that, we basically have these tokens representing the current state of the subnets. If we fire transition A, now only transition B is enabled, and we move to transition to place X. Now C is enabled, and we can loop around, and once again A and B are enabled. Notice that we have only a certain number of possible reachable markings. So initially we have the marking UW, so the marking here turns into a place, and transition A is enabled and transition B is enabled. If we fire transition A, we will move to a new marking V and W. If we, on the other hand, we fire B, then we'll have marking U and X. Now we must fire the alternative action, so after A follows B or after B follows A, and at that point we reach the marking with V and X, and the only thing possible now is that C can fire. Notice that the finite state automaton on the right hand side perfectly models exactly what's going on in the PetriNet on the left. So that means that some PetriNets can be modeled by finite state processes. The question for you is, which are the nets that cannot be modeled by finite state processes? Which are the ones that can, and what's the procedure for converting such a net into a finite state process? After seeing this example, you should get a pretty good idea, however. Most mathematical models of computation are equivalent to Turing machines. Interestingly, PetriNets are not. They're not computationally complete. And there is a non-trivial proof of this. In particular, it turns out that PetriNets cannot model testing of the value 0, and they cannot model priorities. But there are various extensions of PetriNets, and as is typically the case, if you have a model that is not Turing complete, adding one tiny little thing usually does make it Turing complete. So here's an example of a so-called zero testing net. It looks just like a regular PetriNet, except there is a new kind of arrow here. And this arrow, instead of having an arrowhead at the end, has a little circle, and it wants to test the transition D can only fire if the place it's connected to is 0. That is, it has no tokens. So it just does a test, it doesn't consume anything. So this PetriNet is not modeled, the zero testing net cannot be modeled by a regular PetriNet. We have an equal number of A and B transitions that may fire as a sequence during any sequence of matching C and D transitions. So here the idea is A fires and then B fires. C can fire, but D can only fire if this place is empty. So that means A must be followed by B. There cannot be an intermediate D transition. So this is something that you cannot model with a direct PetriNet. C fires, C is still enabled, D can fire, but it doesn't. So A fires, and now D cannot because it's disabled. So now if B fires, D once again is enabled, and so on. So as a consequence, the number of A's can be greater than or equal to the number of B's, and the number of C's can be greater than or equal to the number of D's. There are lots and lots of different variants of PetriNets. For example, colored PetriNets use colored tokens that represent different kinds of resources. As we saw earlier, we had in our mutual exclusion example, we had some tokens that represented flow of control and another token that represent either semaphore or shared resource. So you could color those in different ways and in order to distinguish them. But you could also have places that have multiple tokens with different colors in them. There are also augmented PetriNets. So these are PetriNets that additionally depend on various kinds of external conditions. Augmented PetriNets have also been used in the context of database systems to represent so-called active databases. In an active database, there are additional rules that can be fired if certain conditions arise. This is typically used, for example, to check integrity constraints. When a certain update is made in a database, you want to check that certain constraints still hold over the database. And the checking of these constraints can be triggered by rules which are inspired by augmented PetriNets. And finally, a very important class of PetriNets are so-called timed PetriNets. And in this kind of PetriNet, there's a duration which is associated with each transition. This means that such timed PetriNets are particularly interesting for modeling workflows in real-time settings. For example, where we have machinery and different kinds of processes that have to run in a very synchronized fashion. PetriNets have been used for all sorts of different problems. For example, modeling workflow, modeling hypertext, and evolution of hypertext systems. And I've also mentioned active databases. They've also been used to model the dynamic aspects of active and object-oriented databases. Finally, let's have a look at how PetriNets map to possible implementations. Basically, we can implement PetriNets either in a centralized or a decentralized fashion. With a centralized approach, we basically follow very closely the mathematical definition, and we have essentially a net manager which looks at the state of the PetriNet, figures out which transitions are enabled, picks one, and fires it, and loops around. This is essentially what we were doing up until now. In a decentralized approach, however, the transitions are actually independent processes, and they're like transactions in databases. They try to acquire the shared resources in their places and try and grab these tokens as a transaction. As you can imagine, then if this cannot be done atomically, there may need to be some kind of rollback action. So if there are competing transitions that try and grab tokens, if they're not able to do so, then we may have to roll back and try again. The centralized scheme is pretty straightforward. The net manager basically loops around. It identifies which are all the enabled transitions. If there are none, then the PetriNet is deadlocked and we terminate. If there are some, then we'll pick a transition and fire it, giving us a new marking, and we loop around. Possibly, we may detect multiple transitions which are independent and fire them concurrently. So then you loop around, and instead of firing one transition, you might fire multiple ones. So there are all sorts of variants of this very simple and basic scheme. In a decentralized scheme, the transitions are processes and the tokens are resources held by places. So the transitions could be implemented, for example, as thread per message gateways, so the same transition can be fired more than once if enough tokens are available. So here the idea is, on the left-hand side we see a PetriNet, on the right-hand side we see processes A and B which are trying to get X and Y. Obviously this should ring some alarm bells, because if this is not done in a careful way, we could reach a deadlock situation. So you will either have to ensure that no deadlock is possible, for example, by always acquiring tokens in a strict and consistent order, or alternatively, you may need to detect deadlock and force a transition to roll back if there's a deadlock. So transitions attempting to fire must grab their input tokens as an atomic transactions, or the net may deadlock. So if A and B are implemented by independent processes and X and Y are shared resources, this is a net that could deadlock. So we would either ensure that deadlock can't happen by ensuring there cannot be any possible cycle, for example, by ordering strictly all of the places, or alternatively we have to detect deadlock and break it. A hybrid solution is to treat the state of the entire net as a single shared resource. So that means that every time a transition wants to fire, it briefly locks the state of the entire net, says, okay, let's do an update, puts it back, and then another transition can compete for that resource. So instead of having a central net manager, each transition process will have the opportunity to update the state of the net as a whole. Now I'd like to show you a brief demo of a PetriNet editor that's built entirely with a Smalltalk-based system called eToys. eToys is designed originally as a tool for allowing children to program in a very simple scripting environment, but the eToys environment is powerful enough that we can actually implement PetriNets in a very nice way. Let me show you a demo. You can find a link to Petit Petri in on the course webpage, and you will find a pointer to a description of how Petit Petri works, and also a link to an interpreter which is running on Squeak.js. So this is an implementation of Smalltalk that's running on top of a JavaScript virtual machine inside a browser. So let's load Petit Petri. Here it's loaded into Squeak.js. And let's have a look at a very simple example. So here's a PetriNet implemented in eToys. And due to some limitations with eToys, we can't represent the tokens as dots. Instead, we represent them as numbers. So here we have a PetriNet with two transitions. This one is enabled because it wants an input from this place, and it'll produce an output back in the same place or in this one. This transition is not enabled because it wants an input from this place as well as that one. So if we try and fire that, nothing will happen. It'll briefly flash orange. This one, if we click on it, it'll consume a token and place one here. This one, if we press it, it'll consume its tokens and then produce an output back here. This one, click and release, click and release, click and release, producing as many tokens as we like. This implementation is also an editor. We have a little factory here which allows us to grab new places and new transitions, and we can connect them, wire them together like so. It's a little bit fussy sometimes, so sometimes it's not so easy to run these guys. So this guy can run over and over again, but if we fire this guy, then eventually the whole net will die. We have quite a few other examples that we've seen before. For example, here's our purely concurrent PetriNet with two independent subnets. Here's our mutual exclusion example. And so on. Here's one that's a little bit more interesting. It's dining philosophers modeled as a PetriNet. Here we have 5 philosophers and 5 forks. Each fork is represented as a place. So they're all available here. We have 5 forks, and we also have 5 philosophers. Each philosopher tries to grab its left fork first, and then grab its right fork. Notice we have consumed these 2 forks, and at the same time, we're at a state where we can start eating. So now when the philosopher has finished eating, the philosopher puts the 2 forks back. Once again, the philosopher can grab a left fork, another philosopher can grab a left fork, and so on down the line. But now we're in a situation where all philosophers have grabbed the left fork, they're each trying to grab a right fork, and now the system as a whole is deadlocked. So this is quite a clear illustration of the problem of deadlock, and it corresponds to reaching a marking in which no transitions are enabled anymore. Here's a transactional version of dining philosophers, which solves the problem of deadlock. And in this case, we have hungry philosophers that grab 2 forks at the same time. So now there's no possibility of looping, so we can have 2 philosophers eating, and then once they place their once they finished eating, they place both their forks back. So in this case, no deadlock is possible. Here's a slight extension to Petit Petri. Here we have additional transitions which fire automatically. Notice the rectangular transitions are fired manually, and the square ones, whenever they're enabled, they continue to fire. Here's an example of a game that's implemented as a PetriNet, namely the star game. The idea is to get all of the tokens out of the yellow places and into the places that are empty now, the purple ones. And the trick is to get everything to turn purple, which is not so trivial. I'll leave that to you as an exercise. Now, the eToys system allows you to take graphical objects like these little squares and rectangles and text objects and script them. Here's the complete implementation of Petit Petri in eToys. It consists of 9 little scripts, and the scripts are related to transitions and places. Let's start when you click on a transition. When you click on a transition, if the color of the transition is green, then we're going to try and, so a green transition is one that's enabled. So we're going to tell all of our predecessors, the places, to decrement themselves. And on the other hand, if my color is not green, then that means I'm red. That means I'll temporarily turn orange. After mouse down, I'm going to tell all of my places to decrement, and that happens. And then a place that has been decremented, it's going to check if it's empty. If I check if I'm empty, then I'll change my color to white. So from being a yellow place, it becomes a 0 value and becomes white. So I have some visual feedback. After checking that I'm empty, if I'm empty, then I'll tell all my successors, hey, you're disabled. Because if I'm a place that's empty, any transition that wants me as an input is no longer enabled. So now I tell my successors, these transitions, that they're going to turn red. Now the rest of the logic is when I release the mouse. So when I go mouse up, then I'm going to tell all my successors, output, to increment. Then, once I increment, I change my, each of the places will change its value to 1 greater. The color changes back to yellow if it wasn't already. And now I'm going to tell all my successors, all the transitions that follow me, hey, you better check if you're fireable. And how do I do that? Well, I simply optimistically assume that I'm fireable. So I turn myself green. And then I tell all of my successors, all of my predecessors, hey, please check if you're empty. And if one of my predecessors is empty, then it'll turn me red again. So this is the logic that will completely update after mouse up and turn all the transitions that are now fireable and turn them green. And if they're not, they'll stay or turn red. Okay, that's everything I wanted to show you today. Lots of different examples with PetriNets. We've seen how we can model very interesting properties with PetriNets, and in particular, we have similar notions of liveness and deadlock as we've seen with finite state processes. However, we have a somewhat more powerful model that can express things that we can't with finite state processes. Thanks for your attention.